there's no expectation that our students do this at all. This is all on them just volunteering to do it because of the pure passion or joy that they are finding or something that they're interested in. So again, people are here today for no other reason other than that. And I know for a couple of them who are seniors here, they can't even put on their college stuff, which is great because they're so I do want to introduce a few special guests that we have tonight. So first person we have that I'm going to talk about is our former MA Math Department Chair, Anita Madison is here. We have the former MA Math teacher and the founder of Math Night, Rich Clear. And we have former MA student, and some of you probably have seen his Math Night presentation on Mirrors, and I know three-time presenter William Brandon is here as well. I know some of you might be potentially we might be doing a virtual thing. We're not sure if it is working or not. If it is working, then awesome, great to see you. So again, super thrilled that everybody's here. I know nobody wants to listen to me anymore, so I'm going to be kind of done rambling on. We have 5 presentations today. We'll do 2, half of one, break, half of one, and then final 2. Sound good? So hopefully around like 8:30ish or so, we'll be out of here, and I'm going to ask Anya and John to come on up and introduce our first presenters.
Hi everyone, I'm Anya.
And I'm John. And last year, Anya and I did a really great job introducing a couple of students. Right, Anya, what's the probability again this year?
Oh man, if only there was a way we could calculate that. Without further ado, here to give us maybe a way to calculate it are Kylan and Kaylin talking about probability of probability.
Probabilities of probabilities. I'm Kylan. That's Kaylin. I would like to welcome you to Math Night. So let's start with a scenario. You're a freshman going into some form of geometry at this school, and you see that you need a compass. So naturally, you go onto Amazon and you see 3 listings for compasses. One has 100% positive ratings with 10 reviews. A second has 96% positive ratings with 50 reviews, and a third has 92% positive ratings with 22,000 reviews. Now, it's important to note that a rating is either positive or negative. We're working in a binary system here. So our question is, which seller will probabilistically provide you with the best experience? Is it seller 1? Does anyone have any? Raise your hand for seller 1. Anyone would say seller 2? 1, a couple. Or is seller 3? That's a lot of you. So some of you are going to be wrong. So I recommend paying attention and you'll find out. Great. Here's a little table of contents to kind of show you where we're going. Well, we started with a scenario, so we can cross that off. Then Kaylin's going to do a lot of the heavy lifting here and show a lot of the math using Bayes' theorem, binomial distribution formula, and we're going to highlight a problem with the difficulties of continuity and dealing with probability. A cool example. Then we're going to come back, bring everything full circle, and then show you a cool little trick that you can use going forward. So sit back, relax, and enjoy some math.
All right, so let's begin with Bayes' theorem. So let's just first ask, what do we want in this scenario? We're trying to ask, what's the probability of having a good experience, right? And what information we're trying to base that off of is the seller information that we have, right? So if we set it up in this equation here, that P is the probability of, and then our A here is the probability of having a good experience. And importantly, this is on the next trial. So if we take our second seller, for example, there's 50 trials already. This is the 51st trial that we're looking at. Are you going to be having a good experience there or a bad experience? That's what we're asking. And our B is going to be all our known info about a seller. So we just look at that page and we see our info, the 4.8 stars out of 5, 50 reviews. And that line in between them means given. So if we reformat this, we have the probability of having a good experience, hence probabilities, given all of our known info. So that's what we're looking at. This is how we're going to set up Bayes' theorem. So let's look at the full Bayes' theorem now. We've got this part covered, right? This is a probability of seeing or having a good experience given all of our known info. Now we're going to go through each of these three terms, and the first one will take the longest. After that, it's pretty simple. So what is this actually doing? Ultimately, it's looking forward with this 51st trial, if we continue to use the second seller as an example, by looking back at the information we have. That's what Bayes' theorem is essentially doing. So we've got that one covered. Now let's move on to the probability of B given A. So let's think about how that would reformat given that we know what B and A are. So it's going to be the probability of seeing the known info that we have given the probability of a good experience. And remember, this is looking back. So when we look at that, our known info is that we have 48 out of 50 positive reviews, and the probability of a good experience is 96%. Now this seems kind of repetitive, right? It's two different things that are B and A. In this scenario, seems to be saying the same exact thing, but we'll see that this is not actually the case, and it provides us some very valuable information to actually complete this Bayes' theorem problem. So to solve that, we've got the binomial distribution formula. I know this seems scary at first, but it's actually, each step is pretty simple if we just break it down. So first of all, probability of X over here. It's just what we're using before, the probability of B given A. This second term is the most kind of weird looking, I'm sure. It really is simple though. We've got N, which is the total number of trials. So in this case, 50 trials. X is the number of successes, so 48. And how is this actually calculated? This is trying to see how many different ways you can rearrange those 48 successes in 50 trials. And this is just the notation that they use. And if you want to actually know how to calculate that, it would be n factorial divided by n minus x factorial times x factorial. So that's just going to be one constant that, as we change x, will give us a different output. These next two terms are just essentially the opposite of each other. Here, that probability, or the P is the probability of a good experience, and then X is, again, the number of successes we have. And then that other term is just the exact opposite. 1 minus P is going to be the probability of a failure. N minus X is going to be the number of failures that we're seeing. So now that we've gone through this, using that info, let's see how we can actually calculate the probability of seeing 48 out of 50 successes. So we got NCR of 50, choose 48. That's how you would say that. Then times that probability, times that. And when we actually calculate that, we get around a 27.6% chance of seeing 48 out of 50 successes given a probability of 96%. So this does not actually give us repetitive results with those two differing known info and probability. And we'll see this here when we create a graph of it. Because this is a function of x, we can actually graph it into something that looks like this. You'll see the bar that is at 48 is the highest there, and we've already calculated that to be that 27.6%. But if we graph the other values of x, we can see that they also do have a possibility of happening. So this will provide us good information for working through the Bayes' theorem, but it can also provide us some interesting information by itself. It can see what's the likelihood of seeing a number of successes in a binomial scenario if we already have our probability established. Okay, so that was the most difficult part of the problem. We're done with that, great. So moving on, probability of A is actually very simple. What is this asking? It's the probability of having a good experience given no prior information. We can just say that is equal to 1 because we just can assume they're going to have a 100% chance of giving us a positive experience if we don't see any of those reviews already. So completely done with that already. Done. But are we done overall? Not quite, because we've got this last term probability of B, which unfortunately has us getting into some calculus. Now, this is something called the normalization factor. What it does is it takes this function that we already have and it makes the area underneath that curve equal to 1. So why is this helpful? we're going to have Kylan tell us why.
Interpreting distributions takes a slight change in thinking. Well, but what is that change in thinking? So let's say we have a dartboard. I don't know about you, but I feel like I could hit that dartboard 100% of the time. So there's my 100% of the time. Great. So let's say I'm going to pick a point anywhere on this dartboard. I think I have a 0.01% chance of hitting that point on the dartboard. So as I start throwing some darts, right, and throw some more darts, as our percentage meter starts to fill up and we hit 100%. Great. Well, there's still more points on that dartboard. And if I continue throwing darts, well, everything's broken. You can't have an infinite chance of hitting that dartboard. So that doesn't work. Okay, let's try again. This time, we're not going to assign a value to any point on that dartboard. So as we start throwing darts, well, nothing happens to our percentage meter. So that doesn't work as well. I don't know about you, but I'm a little confused right now. So maybe a graph will help. So let's look at the graph. Well, here's our graph. We have a 100% chance, the area under the curve, of hitting that the dartboard. So if we try to hit, say, this point on the dartboard, well, we can just draw a line, but that also doesn't work because we can't calculate the area of that line. And I think that's our problem, right? That dartboard has an infinite number of points on it, which means that if we assign any positive value to any point on that dartboard, well, you're going to hit a positive number times infinity, which is infinity. So we have to ask a slightly different question in this case. We have to ask about the area or a region on that dartboard because there's only so much area on that dartboard. So instead, I could ask the probability, what are the odds that I hit anywhere in this orange circle? Well, I can draw the line and I can calculate the area between 2 points underneath that curve. And so that's the answer. We can't ask about a specific point on that dartboard.
All right, so now that we have that out of the way, we can see what this normalization factor actually does. You might be able to recognize this up here. This is the binomial distribution function that we've already covered. Now this z variable that we've made here, this is our normalization factor. And it turns this tiny red graph right here, that's our unnormalized function, into this normalized function. The area underneath that curve is now equal to 1. And so that actually helps us, that's going to help us calculate the probability that we want to see, which we're not going to give it away yet, but it's able to be calculated through some calculus techniques. But I mean, we don't want to do calculus to just figure out what seller we should buy from. I'm sure none of you do either. So how do we pick our seller?
It turns out someone already did the hard work for us. Enter this guy, Pierre Simon Laplace. This guy was a French mathematician and is actually the one who proved Bayes' theorem, right? Bayes came up with this idea, but never came up with the mathematical proof. This guy independently did. And in doing so, he came up with something that we now know of as Laplace's rule of succession. And a simple example is, say you have 8 trials, they're all positive. What are the odds that the 9th trial will be positive? Well, you just add 2 trials, you make one positive, you make one negative. And then you recalculate the amount of trials. And another way of writing this is the number of successes plus 1 over the number of trials plus 2, right? So you have a 90% chance of having that 9th trial be a positive one. So let's apply. Seller 1 had 100% positive ratings with 10 reviews. Well, that's just 10 plus 1 over 10 plus 2, which is equal to about 91.6%. Seller 2 had 96% positive ratings with 50 reviews. That's 48 plus 1 over 50 plus 2, or about 94.2%. And the third one, well, is 20,240 plus 1 over 22,000 plus 2. That gets us about, well, it's not really going to change because there's so many trials, 92%. So seller 2 is your winner, and you have the highest chance of having a positive experience buying from seller 2. And the upside is you get to save a couple of dollars as well. Thank you.
I'm Josh. I have the pleasure of introducing our next. This is AI all around us these days. It started out with the question of, how can AI do my math homework for me in a faster way? And they came up with some interesting solutions. So please help me welcome Keo, Caroline, and Aggie.
Okay, so hi everyone, my name is Caroline, and welcome to our presentation on ChatGPT, how it solves math equations, and when we know that it's untrustworthy.
And I'm Keo.
And I'm Aggie. So we have a difficult math problem we need help solving.
So using only the signs of multiplication, division, subtraction, and addition, find out how many integers you can make with 4 fours. And this does not include parentheses or fractions.
So before you get started, I'll give you a quick example. So obviously 4 plus 4 plus 4 plus 4 is 16, and that would be using 4 fours and the simple signs we have up here.
Okay, your 30 seconds starts now. Okay, so time's up. Your time is up, so let's get a few examples from you guys. Let's get 2. Who wants to go first? Just raise your hand. Yeah.
24.
What's the equation? Like 4 plus 4 plus 4.
Like, how did you get to 24?
Yeah.
How many integers you can replace 4 for?
What's an example of an equation? 30 to 40? Okay, well those are guesses on how many possible answers we can get. Can we get an example of the Go ahead.
Me?
Yeah, go ahead.
4 plus 4 plus 4 divided by 4.
Great.
Great.
That's one option.
Let's get
Any
another.
others? Yes.
4 times 4 plus 4 plus 4 is 20.
Great. That's another one.
Okay, so sadly we do not have enough time for everyone to work out all the possibilities. So we are going to use the fastest way to get anything done. ChatGPT.
But wait, isn't that cheating? We can't use ChatGPT to solve this problem, especially not for a math night presentation.
Hey, well, maybe, but we'll check it afterwards with our actual work, and then we'll see if we'll be able to use ChatGPT on our actual math homework.
So this is a screen recording of me asking ChatGPT the question, and I have specified that there are no parentheses or fractions. So I put it into ChatGPT, and then a bit of scrolling. So far, I'm seeing, okay, so it has 18 different answers. Okay. So.
Yay, so ChatGPT solved it. It's 18 answers.
I don't know, let's check to see if these are right.
So to check to see if ChatGPT's answer is right, we found every possible sign combination. So there are 4 signs and 3 slots for the signs to go in. So that would be 4 signs for the first slot, 4 choices for the first slot, 4 choices for the second slot because there's no order, and 4 choices for the third slot. And so then that means it's 4 to the third power of 3, so that equals 64 combinations right here. And so there are 64 sign combinations.
So next, we filled in 4s next to the signs and calculated each answer.
But we noticed that most of the answers were repeats, so we just kind of crossed those out and eliminated them.
and some equal decimals, so we also eliminated those.
So the total answer is 21.
And does this mean that ChatGPT is wrong?
Well, it looks like in the case of human versus robots, the humans win.
Yay.
So why was ChatGPT wrong? Why were a group of sophomores able to outsmart leading artificial intelligence?
Well, to understand this, we first must understand how ChatGPT works. And just a disclaimer, ChatGPT does have some internal calculators for simple problems, but we're not focusing on that right now.
Okay, so let's dive into the internals of ChatGPT.
So this is just a fun fact. I asked ChatGPT what it sees, and first it generated this image, and then I specified what I was trying to say, and I asked it to turn the equation into vectors, which is how ChatGPT basically interprets. And it wasn't able to give me actual vectors, but this is an example of what it would look like. So ChatGPT is a large language model, meaning that it's not made for complex mathematical equations.
So the way it's programmed to generate answers is whatever sounds right with a few twists. While this works well for drafting an email, it does not work well for solving complex and abstract math problems.
Chat is not a free thinker, so the way it solves problems, so the way it answers problems is based off patterns it finds on the internet.
And when writing, it uses autoregressive text generation, which means that it generates the next words based on the words before it.
I know that all sounds a little confusing, so this diagram animation should clear things up.
And just a disclaimer, this is also just an example and it's overly simplified. So first, the user inputs the question into ChatGPT. This is the 4/4 question. And then the parameters inside of ChatGPT assign percentages to the ways that it can start the answer. So you can see here that there's a 20% chance that ChatGPT chooses 4 plus 4 plus 4 plus 4, a 15% chance that it chooses 4 times 4 times 4 times 4, and so on. So in this case, it chose 20% answer, and it does this again. So now ChatGPT has the question, it has the first answer, and using autoregression, it selects the next one. So this happens again, and again, and again, and again, until we have all of our answers. So you have the question and all of the answers from ChatGPT.
So what was the result of Chat using this method to solve this equation?
So clearly we can see that it didn't understand it quite well. There's 2 4s here when I said it should use 4 4s, and also used parentheses even when I specified it not to. This, along with other factors, led to ChatGPT getting the question wrong. So let's try it again. So I'm inputting the same question, it's exactly the same. And, okay.
Not Jeopardy music.
Okay, so it looks like it's still using parentheses, even though I told it not to. And this time it looks like we have 10 different integers, and that's different from the 19 that we had earlier.
So why does ChatGPT yield these contradictory answers? First of all, there's a lack of verification layer, and GPTs are large language models, not symbolic math solvers like Wolfram, to generate text that sounds correct but may not always go through rigorous step-by-step proofs unless explicitly prompted.
And also, it has something called over-accommodation bias. So ChatGPT is built to be helpful, which means that it tends to go along with whatever you say, sometimes a little bit too much. If you confidently suggest an answer or an explanation, the model might agree with you and even build off it. It's basically just trying to be cooperative, not combative.
Lastly, there's no persistent memory or truth validation, so each answer is generated fresh. If you ask the same question twice in different ways, the model may give you different answers unless it is constrained to follow specific rules. This is especially true when you close and change tabs when using ChatGPT.
So how can we know when ChatGPT is right and when can we trust it? So there's a few ways that you can do this. And the first one is asking for a step-by-step reasoning. you can say, please solve this step by step and explain your reasoning, and this avoids hallucinated or black box answers.
The second thing you can do is cross-check with external tools. So for symbolic math, you can double check answers to find your final answers with external tools like Wolfram Alpha.
You can also just challenge the model. If you think it's wrong, you could say, I think you've messed up in this step and you don't have the right answer, or as we've said many times, you can just say you're wrong, and then it'll be like, oh yeah, this is where I messed up, this answer is not correct.
And go ahead.
Yeah, you can also open a new tab, and so you can just open a new tab and compare the answers to make sure they're the same.
And the last one is just do it yourself. Clearly, the best option for how to do this problem was just do it yourself. And that's it. But I just wanted to give you guys a fun fact. We have asked ChatGPT this question so many times that it started off with 60 different answers, and it has slowly started to get to the actual one. Thank you very much.
Hi, my name's Kevin. This is Javier, and we're here to introduce Julian and Griffin, our presenters for the next one. We'll be talking about.
We've been working with them for the past few weeks, not 5 weeks, on cryptography and their insights to it and how they wanted to pursue this more information about it because it was interesting to them and it was interesting for us to listen to. So we're really excited to see them come up here and share what they've learned with you. That's what I do.
Okay, so I'm Julian, and this is Griffin, and this is our presentation on the power of cryptography.
All right, so first of all, Julian, what on earth is cryptography?
So cryptography is basically just using and developing methods that will allow you to encrypt information and basically secure communication between you and another person.
And so we can divide cryptography into 5 basic parts. And that first part is the plain text. So it's the original text is going to be enciphered. And for the example we're going to walk you guys through, we're just going to choose the word curiosity. Nice and simple.
And then the second part is the encryption algorithm. So there's a lot of complicated ones, but for our example, we'll do a really simple one called shift cipher. And basically this just means that we move each letter of the alphabet down or up a certain amount, and then we replace it when we actually write out the information with that number, or with that letter. So in this case, we chose plus 11. So if we take G, for example, we move it up 11, and it correlates with R. So when we write it down, we would write R instead of G. So for C in curiosity, we would write N instead of C. And then the third and probably most important part is the key. So the key is just the key information that is used in encryption and decryption. So in this case, it's R plus 11 for our shift cipher. And there are 2 different types of keys. So there's symmetric and asymmetric keys. So symmetric keys are basically means the same key is used in both the encryption and decryption processes. So in our case, we use symmetric key 11 to encrypt it, and then 11 to decrypt it. So we go back 11 for decrypting our information. And then the other part is asymmetric keys. So asymmetric keys are a lot more complicated because they usually require 2 different algorithms. And basically this means one key is used for encrypting the information and another is used for decrypting. And this is a lot more secure because only one person can know the decryption algorithm, and so they're able to decrypt the information while no one else can decrypt it. And so how do we do this when we're using letters and not numbers? So the first step is that we convert the alphabet to numbers. So here we convert each letter to a number, and we start from A is equal to 0 and Z is equal to 25, and all the numbers in between. And then the second part is writing it out. So C correlates with the number 2, and U correlates with the number 20, and so forth. And then now we need to scramble it up. So in our case, we did plus 11. So what's 2 plus 11? 13. And then what's 20 plus 11? 31. But how does this work? Because there's no letter that corresponds with the number 31. This is where modular math comes in. So this is how modular math works. So we're doing an integer divided by another integer and finding the remainder. So in this case, 5 is what we're trying to find the remainder of. So 5 divided by 4, what's the remainder of that? So that's equal to 1. So we could do 1, 2, 3, 4, 5. So that's the remainder. And so for 20, we would do plus 11, 31, and then do modular 26 for our 26 different letters to get our answer. So that would be 5. And then we do that for the rest of them, and we get all of this. And now we can replace each of these with the letter that corresponds to its number. So all of this information, all of these. So it's just scrambled up. Now we can't read curiosity out of our letters.
All right, and so for the last few parts of cryptography, obviously the last one is ciphertext. So as Julian just showed you, this is the ciphertext we're going to get. So this is the encrypted information that we're going to send. And then after this, we have one more step, which is the decryption algorithm. So as Julian talked about, we have a key, and what you do for the final step is you're going to use that key in the decryption algorithm to turn this jumble back into the word curiosity. So if we just start out with the word N, we can reverse the process, go over 11, and see that N corresponds to C, and then use that to get our word.
Okay, and this brings us back to the key. So how are we supposed to keep the key safe? So that's where the Diffie-Hellman key exchange comes in. So this is basically a way to communicate the key to the other person without revealing what the key is to anybody else. So this is basically the basic equation, x to the y mod z equals something. And basically the two people choose a base and then something they take the modular of. So in this case, we chose 2 and 19. And so imagine I'm here on the left, and this is Griffin on the right. So we both pick an exponent, right? So I picked 8, and Griffin has picked 15. And now we put it into our equation. So I've gotten the answer 9, and Griffin has gotten the answer 12. Now we send each other the answer we got. So Griffin tells me that he got 12 out of his equation, and I tell him that I got 9. Now we both take each other's number. So I take the 12 that he got and put it to my exponent, 8, and get 11. And he takes the one I got, 9, puts it to his exponent, 15, modular 19, and he gets 11. And you see we both got the same thing. That means that our key is 11. So this basically means that we're able to tell each other certain information. So 2, 19, 12, and 9. And that doesn't reveal our key, right? So nobody can work back from these numbers to find our key, while we can create our key using these numbers. And if you try to brute force it, you could solve our key 11 with just these small numbers. But in real life, you would use a lot bigger numbers with really big exponents, so that there are so many different options that a computer can't brute force all the math and get to your answer.
All right. So despite all what Julian talked about, we're keeping the key safe, but we're still fundamentally only taking the alphabet and shifting it over by 11, which is pretty easy to crack. So first of all, who here has ever played Wordle? Yeah, there's a lot of people. Will anyone share their starting word and why they chose it? Yeah, Frank.
Frank.
And that's a great choice. Anyone else?
Why would you use Frank? It's a great word.
Yes.
I do because it has a lot of vowels.
Yeah. How about you, Julian?
I use audio because it has a lot of vowels too. And I know that vowels come up a lot in English words.
Yeah, so both of you guys tap into something really important. So certain letters in the English language are going to appear more often than others. Does anyone have any guesses of what the most common ones might be? You can just shout them out. Yeah, so letters like E, T, and A are going to be our most common ones in English. How about the least common ones?
Q, J.
Q and Z are our least common ones, and then there's the rest of the alphabet. So drawing on this, just keep it in the back of your mind. We're going to use it in a sec. So we're going to come back to this thing, which is a monoalphabetic substitution cipher. So we're taking the alphabet, and we're going to encipher it by randomly replacing a letter with another one. So the example is we're going to take D and replace it with K. So this is a little bit more secure than what Julian's talking about, because it's fully random. There's no way to break this just by looking at it. And so this is a piece of text that we've enciphered monoalphabetically. So just by looking at it, it looks like a mess. If you looked at this, you'd have no clue what this means. But if we go back to what we talked about, we can draw on our information about certain letters appearing more often in English. So there's that chart once again. And if we know that certain letters are going to appear more often, we can begin to sub out the most common letters in the cipher with the most common letters in English. So we can start by some letters that we know are common are E, T, letters in that cipher, E, T, and A. So here, we just did that, and already we're starting to make progress in solving the cipher. And you can continue following this. It's a little bit tedious, but you can also learn to recognize patterns in the words. So for example, if we look at our first word, we have a T and an E, and then this B in the middle. We can use a little bit of reasoning and gather that that B is probably an H, meaning that's the word the. And then we can continue working our way through the cipher and replace all the B's with an H. And so just continuing through that process, you solve it, and you can keep recognizing those patterns and working your way down through the list of the ones that are most common. So eventually, if you keep following that process, you'll get this enciphered phrase. So now that you guys know this, we have a little bit of a challenge for you guys. So this is a longer piece of text. We are moving into our break. If you guys want, we have a little bit of a challenge for you. So this is a piece of text for you guys. It's been enciphered in the way we talked about. So this is how often each letter appears, and then we're going to give you a sheet that has this piece of text, how often each letter appears, and then how often each letter appears in English. Now, hopefully, if you guys are paying attention, you'd be able to solve this. So we're going to go into our break now, and I wish you guys luck.
All right, everybody, so you have some homework to do. I'm not very good at Wordle, and we'll take about 10 minutes.
It's on the table right by the snacks. There's